sounds okay. All right. So making sure the sound is going through properly and everything. Hopefully that wasn't too much double sound for a moment there. So what I'll do is continue with some more physics. I'll be looking at continuing where we were yesterday with the uh, generating function. So we got to the part where they mention what the generating function is, and I may take some breaks throughout. If I take a break abruptly, I'll be back. And but I may see if I can go for 2 or 3 hours or until I figure out exactly what the generating function is. So we know it's this function f. I'm going to read a little bit farther, and then perhaps I'll go in reverse if I don't have it by the end there. Right. So right now we're on page 371 of the text. To show how the generating function specifies the equations of transformation, suppose f were given as a function of the old and new generalized space coordinates. So this is an example that we're doing here. So f equals f1 of q, and t. This is equation 912. Equation 911 then takes the form. So this was 911. So this becomes p I q dot minus h equals, here everything seems to be the same, minus k plus d f1 dt. So now we're going to expand the second part. So it becomes pi qi dot minus k plus partial f1 over partial q dq over dt plus partial f1 over partial big Q big Q over dt plus partial f1 over partial t dt over dt. So this becomes what the book has, which is pi qi dot minus k plus partial f over partial t, because this is just one, plus partial f1 over partial q q dot plus partial f1 over partial qi, and then we have big Q dot. That's the old and new coordinates qi and big Qi are separately independent. Equation 913 can hold identically only if the coefficients of Qi dot and Qi dot each vanish. Saying that Pi must equal partial F1 over partial Qi, and capital Pi must equal partial F1 with a negative sign partial Qi, and thus K equals H plus partial F1, and H is the Hamiltonian, over partial T. And this is 9.114, not 9.14. Equations 9.14a are interrelations defining the momentum as functions of Qj and big Qj and T. Assuming they can be inverted, they could then be solved for the n Q's in terms of Q and P. And T, thus yielding the first half of the transformation equations. Once the relations between the Qi's and the old canonical variables have been established, they can be substituted into equation 9.14b so that they give the NPs as functions of QP, QJ, PJ, and T. That is the second half of the transformation equations. The complete story equation 9.14c provides the connection between the new Hamiltonian K and the old one H. So this connects the new H, old H. Okay. So the generating functions, the time derivative of the generating functions plus the Hamiltonian gives us a new Hamiltonian. Time derivative of the generating function plus the Hamiltonian equals the new Hamiltonian K. We must be careful to read equation, it's a C here, C, A, B. You must be careful to read equation C properly. First, Q and P and H are expressed as functions of big Q and big P through the inverses of equation 9.4. We invert these equations to get Q, P in terms of big Q and big P. Then the Q, I in partial F, I partial T are expressed in terms of big Q and big P in a similar manner, and the two functions are added to yield K. The procedure described shows how, starting from a given generating function F1, the equations of the canonical transformation can be obtained. Having a better idea of what this generating function is, but it's still not completely clear. we can usually reverse the process given the equations of transformation an appropriate generating function may be derived. So equations of canonical transformation and give us the, hey, how you doing? Generating function f1 and reverse. So take a quick break. I shall be back. So that's what I was looking at. Apparently, the equations of canonical transformation, which I'm still actually unclear what that is, um, and the generating function f1 are related. You can go from one to the other. Um, equations of transformation 9.4. And I'm putting that for the for generating function canonical transformations. This process relation. Right. Here we go. So it's saying given equation transformation. Hold up. All right. So this is how we derive 9.1. Equation transformation. So one invert 9.4 so that we have pi of q q t and p I q q t. So that's lowercase and capital case. So now 9.14 integrate 9.14 to get the generating function. All right. But that means that if we have a generating function, take derivative of generating function to get 9.14 to get 9.4 and to invert we get the 9.4 inversion. Invert 9.4 inversion to get equations canonical transformation. All right. So finally, we have some practical methods here. So we want to get a generating function. We start with equation 9.4 and we invert it. So now we have little p in terms of q, big Q and t, and big P in terms of q, big Q and t. So that's momentum. And now we have 914 equations. Now we integrate the 914 equations. That should give us the generating function f1 or f however many. Then we can take the partial derivative of f1 with respect to t, add it to the original Hamiltonian and get the new Hamiltonian in the new system. Conversely, if we have the generating function, we could take the derivative of the generating function. That'll give us momentum. Then we invert. That'll give us an inverted momentum, inverted equation 9.14. Then we reinverse the inversion to get the original canonical transformation equations. All right. Come on to something here. Finding where I was, where we left off last time. Integrated. Oh, I see. In principle, providing the transformation is canonical. So that's important. If not, and as we went over yesterday, the canonical transformation is one in which we would take the matrix in question and transpose it and sandwich the anti-symmetric matrix between the transpose and the original matrix. If we get back the anti-symmetric matrix, then it is canonical. And sometimes they're canonical up to a phase, which means we could just multiply a number to it or divide it by a number, and it'll give us the 0, 1, -1, 0. Thus, f1 is always uncertain to within the additive arbitrary function of t alone, which doesn't affect the equations of transformation. And there may at times be other ambiguities. It sometimes happens that it is not suitable to describe the canonical transformation by a generating function of the type f1 QQT. For example, the transformation may be such that t cannot be written as functions of qt and t. But, all right. I think they're starting to go to uh, a separate idea, which I want to stick with the foundational case. So I may actually skip to the examples. Maybe I should find, okay, right. I'll skip to section 9.3. So everything is less symbolic or abstract. As a final example, let us consider a canonical transformation that can be used to solve the problem of the simple harmonic oscillator in one dimension. And perhaps, well, I guess this is sufficient with just the pad being up. I was about to say maybe I could put the book on the side. What if somebody pops in and you're interested in seeing the book at the same time? Let me know. I can put the book up as well. So for now, I'll keep just the pad up, except I'll switch it, shift it a little bit so that is more centered. Right? If the force, right? So we have a simple harmonic oscillator. If the force constant is k, I'll try to write a bit neater. So those who've been watching the channel, you are familiar with the simple harmonic oscillator and the constant k. The Hamiltonian for this problem is in terms of the usual coordinates. So h is going to be k e plus k e. We need it in terms of p and q, which I think I'm going to do this slightly differently from the book. So let's say that we have spring coming out. This is our mass. This is the base upon which it sits. Spring constant has spring constant K, and it's on the ground X. So we know that the kinetic energy will be 1/2 mv squared, which is 1/2 m x dot squared. You can also multiply this by m over m. Multiplying by 1 doesn't change anything. So now we have 1 over 2m times m squared x dot squared. So that becomes momentum squared over 2m. P equals momentum. So now I have my kinetic energy in terms of momentum, and the potential energy for a spring is going to be the distance, 1/2 the spring constant, and that distance squared. So the spring potential is based upon the distance moved by the mass relative to the spring. It's slightly different than we might normally think of potential energy. So that's 1/2 kx squared. And they're calling AQ to be XQ. So X is defined as Q. So X is our variable that's changing. So that becomes Q. So we know P is the momentum. And Q equals changing variable, or I guess we can call it the generalized coordinate. Because if we were doing what the Legendre method, like it would be the generalized coordinate, right? So that means that since the Hamiltonian is KE plus PE, which is T plus V, that's going to be P squared over 2M plus KQ squared over 2, which is what the book has. So I guess technically I'll do it the book way. I'll just, in case I don't want to change up my symbols and then later it's change adds too much confusion from what I'm seeing in the text. So I'll just keep it the same. But just have to keep in mind that Q is the generalized coordinate or the changing coordinate. I guess just to say changing variable. But there's a better word for that, but I think I need to change my what do I call them thing. Is it good to have that? I'm always thinking about the most convenient way to have stuff. Right. I realized I just changed the damn thing that's there. Like it changes the actual base color too. All right. So we have that. Designating the ratio K over M to be omega naught squared. H can be written as it's interesting what they do. We can look at this for a moment. I'm going to extract so what I'll do actually to make sure I cover all the steps. I'll divide this by M and multiply it by M. So that's the same. So that equals Q squared over 2M plus KM Q squared over 2M. And we'll call omega squared equals K over M. So this becomes P squared over 2M plus omega squared M Q squared over 2, right? Because the K over M here ends up being omega naught squared. So we're left with omega naught squared MQ squared over 2. And what I'm going to do is multiply by another m over m. So we have to multiply by m squared over m squared. So that becomes momentum squared over 2 mass plus omega squared m squared q squared over 2m. So now I can factor out 1 over 2m, and this leaves me momentum squared plus omega squared m squared q squared. And this is what the book has for equation 9.34b. This is 9.34b. Right? So it says this form of the Hamiltonian, that the sum of two squares, suggests a transformation in which h is cyclic in the new coordinate. All right. So now we have sum of two squares is cyclic. So it seems like it's beneficial to get whatever we're working with in a sum of two squares form, if need be, with a constant in the front, if possible. I wonder if it's beneficial to mark 1 over 2m as alpha. Not sure how often it comes up. Let's see. Well, it's good the way it is. If we can find, or it says cyclic in new coordinate. If we could find a canonical transformation of the form this is the part that's probably most unclear. So, book given canonical they have little p equals a function of big P cosine big Q, and then we have little q equals a function of big P over mass omega sine big Q. And this became our 9.35 A and B. And the Hamiltonian as a function of Q and P would be simply so K, all right, so H is in terms of P, Q, and T, and K is in terms of big P, big Q, and T. So K, we saw earlier that K is H plus the generating function. We'll work this out and see what happens. So this is h. The one thing that's unclear in the text is saying k equals to h. And I'll just say, let's scroll back here. K equals h plus a generating function, at least a partial time derivative of the generating function. But perhaps because it's cyclic, the partial derivative of the generating function must be zero. Is what's going on, right? That's what's going on. So k equals h plus that. We call the number of that equation 9.14. So this equals h plus 0, since that's why they must be calling it that in this case. So this is going to be h in terms of q. So little p squared is going to be f squared of p cosine squared, and q squared is going to be fp squared, m squared, omega squared, and sine squared. And if I add these together, we have supposed to be um, k, so this will be 1 over 2m. Let me just copy it down so I can not scroll as much. F squared p cosine squared q plus uh, omega squared m squared f squared of p over m squared omega squared. So that's why they have the m squared omega squared in the denominator to cancel those out. Sine squared big Q, which equals 1 over 2m f squared of p of cosine squared q plus, and we have these two will cancel, sine squared big Q, which equals f squared of big P over 2m. And this is equation 9.36. So that Q is cyclic. Okay. The problem is to find the form of the yet unspecified function fp. I see. So these are chosen to simplify k. And be cyclic. So I suppose we can define these however we want. be Q cyclic. Problem is to find the form of the yet unspecified function fp that makes the transformation canonical. If we use a generating function of the first kind given by, right, so I'm supposed to be learning how to find a generating function and they just give a generating function. I'm not sure how they got it. F1 equals m omega q squared over 2 cotangent q. That seems familiar. Thinking maybe we divided p by q to get the cotangent, but that doesn't explain where the p squared comes from. I mean, the q squared comes from. Because they're saying fp is q squared. I mean, it does work that way. If we do this, if I divide p by q, that equals fp cosine q divided by m omega fp over m omega sine q. That does give me m omega cotangent q, but it still does not tell me about the q squared over 2. Right, so I'm not sure how they got the generating function there. I have p saying p is df of dq of little q. So if I integrate with respect to q, I should get the canonical of the generating function q. All right, let's just keep on going until we get p equals partial f1 over partial q equals partial partial q of m omega q squared over 2, which equals m omega q. Got my cosine, my cotangent q here, and big P equals partial negative partial f1 over partial big Q, which equals partial big Q of m omega q squared over m omega q squared over 2 cotangent q. I don't know the derivative of cotangent. The book gives it, but I'm not sure how they got it. I mean, how I would do it, I'll probably break it up into cotangent, cosine over sine, and then take the derivative of that. But I won't go through that process right now. I'll just say this is m omega q squared over 2 and 1 over sine squared q. So that means that the derivative of cotangent of q is negative 1 over sine squared q, so it's to cancel out our negative sign. 9.38. Right? So solve for q p equals m. For little q and little p. Okay. Q equals p, little p, over m omega cotangent of q, and big P equals m omega q squared over 2 sine squared q, and thus q equals 2p sine squared q over m omega, the square root of all of that. Right. So what I'll do is, like the book does, and plug q into here. We have p equals m omega q cotangent q. Now plug this q into there. So we have m omega sine q, taking the sine out of the square root of 2p over mw. So that's the same thing as saying sine big Q square root of 2p mw, and that cancels the denominator. And that's a big P inside. Maybe I need to make the big P's bold or something. In comparison with equation 9.35a evaluates FP. With that is this. And we also have this from 9.35. That's how we get that. Hold up. Sine. Because I forgot my cotangent Q. The cotangent is cosine over sine, so that just leaves cosine. So that's why f of p equals that. This is 9.40. It follows then that the Hamiltonian in the transformed variables is h equals omega p. The Hamiltonian is cyclic and Q, the conjugate momentum P, is a constant. It is seen from equation 9.41 that P is in fact equal to the constant energy divided by omega. The equation of motion for Q reduces to the simplest form, right? I have to look into this in more depth. So everything seems a bit more clear, but it's definitely not fully understood. I don't feel like I can find the generating function on a separate problem, but I'll look into it in more detail. Perhaps I'll come back on Saturday and do a complete problem, a more complicated problem. Where we get the equations of motion from the Hamiltonian, and I get a generating function. So that'll be the plan for this week. So thanks to everybody who watched later. Like, subscribe if you haven't already. Let me know if there's something else you want to investigate. I may do a topic on that. I do hope you have a good one.